Sophia's Embrace, a study of divine messages delivered through synchronicity.
Inspired by the work of Jason Bickford and Valentinian Restoration.
Look into a mirror, wave your hand and your reflection will wave back at you. In everyday life, it's easy to take the effect of symmetry for granted. But symmetry is vital to understanding and predicting how our universe works. This relationship between symmetry and the mechanics of the universe was something Emmy Noether proved in 1915 with her remarkable theorem, linking maths and physics in one harmonious statement. Wherever there is a symmetry of nature, there's a corresponding conservation law. So what exactly do we mean by symmetry in physics? Well, it can be described as a transformation that leaves a system fundamentally unchanged after the transformation has been performed. It's a change that makes no change. Take, for example, spatial translation. If we have a system and move it to a different point in space, that system would continue to work in the same way, provided all of the relevant conditions of that system were moved along with it. In other words, the laws of physics are not affected by translation in space. And similarly, with time translation, a system can be shifted at any point in time, and its physics would remain unchanged too. Even the most fundamental laws of physics are themselves symmetrical. They remain the same wherever or whenever you are in the universe. The symmetry of time translation confirms to us that energy cannot be created or destroyed, as the total amount of energy in the universe always remains the same, no matter what point in time you're at. Likewise, the symmetry of spatial translation leads directly to the conservation of momentum. And this is the beauty of symmetry. It gives definition to the world by revealing nature's parameters. If nature wasn't governed by symmetry, we'd be living in a world of chaos, where nothing is predictable or repeatable. But if the universe follows the principles of symmetry, why is there so much asymmetry in nature? The state of a system might exhibit a hidden symmetry because of some external factors that affect it, but its underlying laws of physics are still symmetrical. So while the sun's gravitational field has a spherical symmetry, a planet like Mercury can follow an elliptical orbit that changes shape due to gravitational perturbations from neighboring planets. It also turns out that not all symmetries are equal. As physicists peered further into the infinitesimal world of particle interaction, they started discovering some puzzling violations of symmetry that would add to an increasingly rich and complex set of rules through which we view the universe. We now understand these violations to be an entirely different group of symmetries. Local symmetries that affect certain interactions, unlike the symmetries that hold true at any point in space-time. These local symmetries are the cornerstone of the leading theory in modern physics, the Standard Model, which looks at the fundamental forces governing the universe. As we delve deeper and deeper into particle physics, we discover more and more symmetries, each one revealing new clues about the forces behind nature's most fundamental interactions. Eventually, we may be able to find a theory that unifies all of the fundamental forces. Whether one exists or not, the search for new symmetries continues to have a profound role in explaining the structure of our universe.